In our previous video, we did our first example of a multi-step synthesis problem. And multi-step synthesis problems are traditionally the problems that many organic chemistry students have trouble with. It's very hard for them a lot of times to take a starting product such as this simple acetylene here and convert it over into a product that is much bigger and much more complicated as far as elongating carbon chains and putting functional groups on them, because it requires them to not only go back and think about all of the other reactions that we've talked about to this point, but the proper order which we should actually add these reagents to make this product. So it is very complicated, and we're going to have to do more than one example, of course, to feel comfortable with it. So here is another example of a multi-step synthesis problem, and let's take a few minutes and work through it. So here we're given a problem, and it looks like we're starting with ethyne, E-T-H-Y-N-E, or aka acetylene here. And we want to take acetylene and we want to add any kind of reagent that we can. It's fair game, open book. Any reagent that you want to add, or series of reagents that you want to add. And we want to end up with a product that looks like this. So CH3, CH2, CH2, CH, CH3 with a Br hanging off of this second carbon from the right. Well, let's name this just to review a little bit of IUPAC nomenclature. Our longest carbon chain is 1, 2, 3, 4, and 5. So this is a pentane because it's all single bonds across the board. And then I've got to give this bromo group a number. Do a number from the left or do a number from the right? And the answer is I'll number from the right because that's closest to the end. That will give me the lowest number. So at carbon number 2, I see a bromo group. So 2-bromopentane. So we need to know, how can we take acetylene gas and convert it to 2-bromopentane using the reagents that we have talked about in mainly the alkyne reactions? Well, first and foremost, let's just do a plan of action here, and I'm going to come over to the side and think about what we have to do. And the very first thing that I notice is that the carbon chain is elongated. So if I take a look, this is a 2-carbon chain, and here we've got a 5-carbon chain. So number 1, I know that I have to elongate. Number 2, not only do I have to elongate the chain, but I will still have a triple bond in place when I elongate. So I'm going to have to take my triple bond and I'm going to have to get rid of it because my product does not have a triple bond there. Not only that, but I have to put a bromine on it as well. So step number 3, I'm actually going to see an addition of a bromo group. So I need to add bromo in some form, in some fashion along the course of the way. So there's a couple of steps here that we need to walk through, that we need to really understand before we go further and do even more complicated examples. So let's start off with number 1. I know I'm going to have to elongate the chain. So now I have to think about what reagents can I use to actually elongate a carbon chain for me in organic. And we've talked about that. We said that in order to do this, we need the acetylide ion and we need some kind of alkyl halide that we need to bring into the picture. The acetylide ion will serve as our nucleophile, and the alkyl halide will serve as the carbon source to allow us to add on more carbons. So if I go over and take a look at the acetylide ion step, well, I'm starting off with acetylene. And we said in order for this to happen, we need to add sodium amide to the system. And when we do that, we we get a removal of one of the hydrogens. And that's good news for us because that's the very first step in chain elongation. So our very first step that we need to incorporate is the sodium amide that it will rip the hydrogen from one of the sp carbons in the triple bond, and we're left with this ion now that we can then turn around and react with some kind of alkyl halide. Okay, so this serves as a two-carbon chain here. So if I kind of want to imagine two of these carbons being taken up, which ones? Well, it doesn't really matter at this point. Just two of these carbons basically are taken up by the acetylide. Well, how many more carbons do I need to add into the picture? Well, I need 1, 2, and 3. I need to add 3 more carbons. So if I start off with a 2-carbon chain, how many carbons do I need to add to get to a 5-carbon chain? Well, I need 3. So CH3, CH2, CH2. There's my additional 3 carbons. But I've got to put a halogen on it, typically a bromide or a chloride, in order for this thing to work. And now we can talk about mechanisms if we want, or we can draw the straight product. And this is carbon, triple bond, carbon. And this carbon hooks up with this carbon, because that's the carbon that's on the bromide or the halogen. So C, triple bond C, and then we've got CH2, CH2, and CH3. So now I've elongated my chain. I've now taken a 2-carbon chain and have elongated it to 5, which is what we needed up here in the product. So step number 1 is taken care of. Okay, so now step number 2 says that once we elongate the chain, we're going to end up with a triple bond. And we see that triple bond. That triple bond is right here. And if we notice in the product, there is no triple bond at all. So we're going to have to get rid of it. And there's a couple of ways that we can get rid of it, but that's good news because look at what we need to add on. We need to add on a bromo there. So we need to add on some type of bromo group. And in order to do it, I need to figure out what type of reagents to add onto that organic. Okay, so I need to get rid of the triple bond, and I need to add on bromine in some form, in some fashion, in order to get to that product. Well, if we look, we've got 2 choices here. We can redraw the product, CH2, CH2, CH3. And I need to add on a bromo group, but I need to get rid of the triple bond as well. Okay, well, if I add on HBr in this step, what my product formation will be is a triple bond C, CH2, CH2, CH3. My HBr will target the triple bond and convert it to a double, and 2 sites of attachment will open up, one here and one here. My H plays with the other H's, so that means it goes over to the left, and my bromo goes onto the other spot, so that goes here. Okay, but this is not the product that we're after because this now still has a double bond involved. So I really want to make it clear, and I want to control it because I don't want more HBr to target this double bond and break the double bond and add another bromo on. So I'll traditionally write 1 mole up here at the top when I can. So now I'm going to take that product that we've just made, the alkene, and we've got to do something else to it because we've got to get rid of that double bond. So what can we add to keep everything the same but get rid of the double bond for me? Well, if I just want to take that double bond and convert it down to a single, the only option that I know right now is H2 and platinum. So what will happen is that we will have a product, and I'll just redraw it again, with a double bond and that H2 platinum will target the double bond and convert it to a single, and 2 sites of attachment will open up. H goes on one side and H goes on the other. So we can come down and clean this up a little bit. This C with 3 hydrogens on it is CH3. This carbon is CH with a Br hanging down below. And then CH2, CH2, and CH3. And you're probably wondering, well, that's not what we wanted. What we wanted was something that looks like this, the bromines over here on the right. Well, we called this 2-bromopentane. Well, let's just name this to see what we would end up with here. So longest carbon chain, 1, 2, 3, 4, 5, pentane, and then on the second carbon, a C-bromo group. So it actually is the same structure.